Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd edition by Briggs, Cochran, and Gillette. I want to work an example of determining whether or not a function is differentiable at a point. And so our question here is, I have f of x, which is a piecewise function. It's defined as 2x minus 2 when x is less than or equal to 1, and it's defined as x squared minus 1 when x is greater than 1. And our question here is f differentiable at 1? And I want to work through our process and I want to create a real quick checklist for what we're going to do. Number one, is f continuous when x is 1? Number two, are the derivatives on the left and right the same? Which is another way of saying that is, are there corners, or is there a corner? And is the derivative defined? No infinites, that's bad. Okay, so we're obviously going to have to go to another sheet of paper now that I have done this. So my first thing I need to do is I need to check that the limit, or that the function is continuous. So I've got 2x minus 2 if x is less than or equal to 1. I've got x squared minus 1 if x is greater than 1. And what I'm going to do here is I'm just going to go in and I'm going to check all my stuff. Number one, f of 1 is 2 times 1 minus 2, so 2, which is just 2 minus 2, or 0. And what I need to see is the limit from the left and from the right the same. And please note that I'm using 1 because, number one, that's where we're looking, but I'm using this rule because I'm saying it's less than or equal to here. Now, so what I have to do then is I have to say is, when I plug in 1 here, do I get 0? So I've got, so the limit, because this is also the limit from the left. So I just have to check from the right. So as x goes to 1 from the right of f of x would be the limit as x goes to 1 from the right, x squared minus 1, which here I can just plug in because that's a polynomial, so I've got 1 squared minus 1, 1 minus 1 is 0. So the limit from the left, the limit from the right, and the function value are all the same. F is continuous at 1. Now, here's where this is going to get gross. I have to evaluate the limit for both of these at 1. So, first of all, I'm going to be a little tricksy here. The derivative of this, because, so f prime of x on this side is going to be 2 because it's a line and that rate of change is the same. So I'm going to cheat a little bit and I'm going to say that on the left, f prime of x is 2. But now I got to come over here and I got to figure out what's f prime of x on the right. This is really bad notation, but I need you to just bear with me because I don't want to go into the actual notation for it because we don't usually write it quite like that. So what I need to do is I need to figure out, and I'm going to come back to this sheet here in a moment, I need dy dx evaluated at x equals 1 for y equals x squared minus 1. It doesn't really matter which definition we're going to use. I'm going to focus on the traditional definition just because I think that that's the one that we're going to use more commonly. So time to work out this derivative. So we'll start by evaluating dy dx, and then we'll just plug in 1 at the end, is the limit, h goes to 0, f of x plus h minus f of x over h. And f of x is x squared minus 1, so that gives me the limit as h goes to 0, x plus h squared minus 1 minus x squared minus 1 all over h. Now, real quick, we're going to say, hey, look, -1 minus -1, 0. Don't have to worry about it. So now I have to do that wonderful expansion. So I've got the limit h goes to 0 of x squared plus 2xh plus h squared minus x squared over h. X squared minus x squared is 0, giving me limit h goes to 0, 2xh plus h squared over h, which is the same as the limit h goes to 0 of h times 2x plus h over h. I've got an h top and bottom, so for our purposes, since it's a limit, the h's cancel. And I have the limit as h goes to 0, 2x plus h, which I just now, this is a polynomial, so I can just plug in. Sorry, I need to make sure you can see that. Just plug in 0 for h, so I've got 2x plus 0, which is 2x. So dy dx is 2 times x, and here, so I'm evaluating when x is 1, so dy dx when x is 1 is 2 times 1, which is 2. So on the right-hand side, my derivative is 2, and we said on the left-hand side, my derivative is 2. And I talked about how this isn't how we normally write this notation. We actually usually don't talk about this notation in terms of this. What will happen later on is we will start writing f prime of x. Actually, I could do that. Why don't I just do that? Is I would say this is linear, so f prime of x is 2 if x is less than 1, and it's 2x if x is greater than 1. And the question here is, I don't know why I went to all this trouble to write this over here when I'm really saying this. Just like we did in that first one, if it's a line, the slope, m, is this value. So I kind of cheated on that one. If you don't believe the derivative 2x minus 2 is 2, go ahead and work out the derivative like we just did for x squared minus 1, and you're going to find that it's 2. Now, I've got this, but notice here, up here I've got less than or equal to 1. Up here I've got less than or greater than strictly, and the question is this differentiable at 1? And so our question here is f prime, if I plug in 1 here, I get 2. So it's 2 here, it's 2 coming in on the left, it's 2 going out on the right. So my only conclusion is actually it is differentiable at 1 because these two things are the same. That's why I wanted to really emphasize here. On the left of 1, the slope is 2. On the right of 1, it's also 2, which means that there's no corner. It's nice and smooth through there. And I want to talk about real quick what that graph looks like as this video wraps up. Just a real quick sketch. Now we said that the function value, so I have f of x is 2x minus 2 for x less than or equal to 1 and x squared minus 1 for x greater than 1. So here's 1. So I've got a straight line doing that. And then to the right, I have going x squared minus 1 there and 2x minus 2 here. But what happens here is, over here, my tangent line is actually exactly the same as that function. And then as I come out, the tangent line at 1 doesn't change, and it's still 2. And that's why we can say that it's differentiable, is through this point, the slope doesn't change. And that means that we're differentiable at 1. I hope you found this video useful. Good luck in our semester.